Welcome to section 11.4, Adding, Subtracting, and Multiplying Radicals. In this section we have two fundamental ideas. The first, when adding and subtracting radicals, is that you combine radicals using the same property for which you combined like terms, namely distribution. However, it may be necessary to first simplify the radicals to see that you do in fact have like terms. The second fundamental idea is that when multiplying radicals with the same index, this is done using the product property for radicals. When combining radicals of different indices, it is necessary to use fractional exponents. But it is unlikely that you will see problems of that nature in this section. Example 1. Let's simplify 5 times the square root of 7 minus 4 times the cube root of x plus 6 times the square root of 7 plus 6 times the cube root of x. We first observe which terms are actually like terms. We see that 5 times the square root of 7 and 6 times the square root of 7 are like terms. In addition, the negative 4 times the cube root of x and 6 times the cube root of x are also like terms. Manipulating the variables, or manipulating the terms so that the like terms are together, we have 5 square roots of 7 plus 6 square roots of 7 minus 4 times the cube root of x plus 6 times the cube root of x. Factoring out the common term of square root of 7, this leaves us 5 plus 6 times the square root of 7. And factoring out the common term of the cube root of x leaves us with negative 4 plus 6 times the cube root of x. 5 plus 6 gives us 11 times the square root of 7. Negative 4 plus 6 gives us 2 times the cube root of x. For the second example, suppose we are asked to simplify 3 times the cube root of a to the fourth b squared plus 3a times the cube root of ab squared. In this case, we have to begin by simplifying the radicals, because as they are not like terms. Simplifying the cube root of a to the fourth b squared gives us a times the cube root of ab squared, while the cube root of ab squared is fully simplified. Now that we do have like terms, 3 times the cube root of a to the fourth plus b squared plus 3a times the cube root of ab squared, when simplified, gives us 3a times the cube root of ab squared plus 3a times the cube root of ab squared. Factoring out the common term of the cube root of ab squared gives us 3a plus 3a. Combining like terms gives us 6a times the cube root of ab squared as a final answer. As our third example, suppose we are asked to multiply and simplify, assuming that the variables represent positive real numbers. The square root of 16m to the 7th n to the 9th times the square root of 3mn squared. Both indices are the same, so we are able to use the product rule for radicals. We combine both terms. We multiply both radicands under the same radical to give us the square root of 16m to the 7th n to the 9th times 3mn squared. Using properties of exponents, we see that this is equal to the square root of 48 m to the 8th n to the 11th. Now we are able to simplify. 48 breaks down with the largest perfect square dividing it is 16 times 3, while m to the 8th and n to the 11th, when we divide the index by the power on m, we see that 2 goes into 8 4 times, so we have a power of m to the 4th on the outside, with remainder 0, so we have no m under the radical. 2 goes into 11 a total of 5 times, leaving a remainder of 1, so that we have 5 n's on the outside and 1 n under the radical. This gives us a final answer of 4 m to the 4th n to the 5th times the square root of 3n. Suppose, for example 4, we are asked to multiply and simplify the cube root of y times the quantity 3 times the cube root of y minus the cube root of y to the 5th. Using distribution, we multiply so that we have the cube root of y times both terms in parentheses to give us the cube root of y times the cube root of y minus the cube root of y times the cube root of y to the 5th. Then using the product property for radicals, we have the cube root of y times y minus the cube root of y times y to the 5th. Using properties of exponents, this gives us the cube root of y squared minus the cube root of y to the 6th. Now simplifying each of these, the cube root of y squared is fully simplified because 3 goes into 2 0 times, so we have no y's on the outside, with remainder 2, so the y squared remains under the radical. For the cube root of y to the 6th, 3 goes into 6 2 times, with remainder 0, so we have a y squared outside the radical and no y's under the radical. Therefore, if we have a final answer of the cube root of y squared minus y squared. For our final example, suppose we are asked to multiply and assume that the variable z represents a positive real number, the quantity square root of 13 minus the square root of z times the quantity square root of 13 plus the square root of z. Using distribution, or FOIL if you prefer, we multiply the terms out to give us the square root of 13 minus the square root of z times the square root of 13, the square root of 13 minus the square root of z times the square root of z. Distributing again, this gives us the square root of 13 times the square root of 13 minus the square root of z times the square root of 13. For the second term, we have the square root of z times the square root of 13 and the square root of z times the square root of z. Now the square root of 13 times the square root of 13 is just 13. The square root of z times the square root of z is z. And using the product property for radicals, we're able to combine these two to give us the square root of 13 minus the square root of 13z plus the square root of 13z. Once again, combining like terms, which at this point should remind you of the difference of squares, we end up with a final answer of 13 minus z.